one, which is FEA. Right, finite element analysis, and of course, finite element analysis is an interesting idea. The fundamental notion dates from, well, probably predates it, but we really started thinking about this seriously, really in the 40s after World War II. And the notion was, of course, that we have complicated geometries that really get beyond what we can deal with in our manual calculation methods, right? They just get ugly, right? I mean, real parts get ugly. They're not nice, they're not constant cross-section, they're not slope changes in geometry, they're stress concentrations and other kinds of nastiness that don't really know how bad they are. So the real world is more complex than we would like it to be. And so there was a desire to try to solve this, or come up with methods of solving these more complex problems. And the approach that was taken is very much in keeping with our engineering mantra. That is, what do we do? What did we teach you how to do in machine? Well, not in just in machine design, but in statics and strengths and everything else. We take big, complex problems and we break them down into little problems that we know how to deal with, right? And then once we solve the little problem that we know how to deal with, right? And once the little problem we know how to deal with is solved, we try to put those back together in a way that makes sense. Okay? Now, this is exactly what we do in FEA, right, in our finite element analysis. What we're going to do is we're going to take big, ugly geometry, and we're going to break it down into simple geometry that we know what to deal with. Okay, we're going to solve the simple geometry, and then we're going to hope that we can put the pieces back together in a way that makes sense. Now, the only thing about FEA that we tend to do is we tend to do this algorithmically. We tend to have a computer break these down. And of course, if we have a computer break these down, the computer never makes mistakes, so the computer was always right. And if anybody in here believes that, okay,
Computers don't make
then no, computers make mistakes too. But yes, if anybody believes that the answer is right because their computer says so, your odds of passing this class are slight. Okay, because as I will discuss oftentimes in this class, as long as your FEA model is defined, is constrained and defined sufficiently that it doesn't go shooting off into space, it will give you an answer whenever you push run. It's just my mantra is that answer is almost always wrong. And by wrong, I mean not mathematically wrong. It's wrong in the sense that it isn't representative of how the part is going to behave in the world. And so we spend an awful lot of time in FEA. There are many, you can push it down too. There's lots of cord on those, Jimmy. They both of them have lots of cord, so they're supposed to be in the middle, but that's okay. The power strips are supposed to be in the middle, but there's lots of anyway. Back to the FEA. There's the tricky part of finite element analysis is not making the models. That's trivial. Okay. It's not even really figuring out what the forces are on the models. We almost can't scare you with statics anymore. demonstrated I could still scare some people with statics, right? Okay, so I shouldn't be able to scare you with statics anymore. Can I phrase it that way? Okay. That I shouldn't be able to terrorize people with statics. However, we actually have to, as we'll see, we actually have to fix the objects in space somehow, and that oftentimes, in and of itself, enforces unrealistic constraints on the model, and we have to learn how to sort of deal with those. Okay, so what we're going to do, of course, is we're going to take large objects, take geometry, right? Some sort of, we have lots of different kinds, but let's say we take some solid geometry, okay, which is where we're going to start, just because we have solid modelers, right? And we're going to decompose this geometry down, right, into components, right? And we're actually going to decompose the geometry down into elements. And then those are going to get decomposed down into points, which we call nodes. How about if I can actually spell today? Okay? And a node is a point in space, that's all it is, just a physical location. And as a practical matter, the nodes are the only place in the model that we actually do mathematical calculations. So what we basically do is, you might think of as we scatter, over the course of our strength and machine design courses. What have we done? We've done a lot of stress analysis at points, right? We look at particular points. What's the bending stress? What's the torsional stress? Right here. We're going to do exactly the same thing, except we're going to look at shear stresses and normal stresses. Exactly the same thing, except the computer's going to figure out where the points are. That's all it is. And they're just nodes. Now, when you see nice, fancy colored pictures and all the rest of it, you're going, wait a minute now, it's not just calculating the points. Yes, it is. And it's interpolating the color between those points. It only has calculations for the points. Okay, for Pacific. Anything else is an interpolation on top of that. Now let's sort of talk about a little bit about how they do this. So let's talk with a beam. Start with a beam element. And what we can say is we have a couple of nodes, right? We have number 1 and number 2 over here. Those are points in space. That's all they are. And we're going to say, oh, this is a node. This is an element. Okay? And so this is the element. Let's call it number 1. And the element is a collection of nodes. Maybe 2, maybe 3, maybe 4, maybe more. It's a collection of nodes for which we know a mathematical relationship. Okay, so that we know how these nodes, these points in space, respond or reflect each other. So if this is a truss element, right, then all I can have on it is forces, right? Some forces, right, that are pulling on it, right? I may fix one point and not have to wait, but have some forces that are pulling on it. And I can say that the displacement is equal to FL over EA, right? Right, that is a displacement. I can rewrite this in terms of solving for the force. I get force is equal to EA over L times the displacement. Okay. And then, of course, we recognize this as we can call this thing K, and we get this is equal to some K delta. Okay. So what we have here, this is an equation, sometimes known as a shape function, for this element. Right? It describes that if I have the forces on these, I can calculate displacements of this node here, reference to this one. Usually the way it's done. And if I put more and more and more of them on there, I can chase this out in space. Now, I've done this in one axis, right? In general, there are three, we live in a 3D world, so instead of having one equation like this, what am I going to get? I'm going to equation like this in X, and I'm going to get an equation like this in Y, and I'm going to get an equation like this in Z. That sounds like fun, doesn't it? So for one simple element with two nodes, I've already got three equations. Okay. And it's actually a beam element. Okay. Then it's not a truss element. If it's a beam element, what's the difference between beams and trusses? I think you're on the right track, right? What's the beams carry moment loads. Trusses only carry axial loads, right? When we have trusses or two-pin connections, right? Or ball joint connections, they only carry axial loads. If you know the two nodes, the forces are aligned with that. They're not. We basically present them. Beam, we have moment loads on this, right? Some sort of moment load on this thing. And so now it carries bending loads, right? So it not only can it deform axially, but it can bend rotationally. And guess what? It can bend rotationally about the x-axis, or about the y-axis, or about the z-axis. And so, once again, we're going to get an equation for the bending about the x-axis, and the bending about the y-axis, and the bending about the z-axis. And so that's going to give us, for this one shape function, one element, it's going to give us 6 equations. Now, does anybody want to solve those 6 equations simultaneously? No. That's why we have computers. Okay, because that's the one thing they're good at, is solving those big matrix equations. These get really big really fast. Right? These problems get really big really fast. It's not unusual to have problems with tens of thousands of nodes. Okay. And for each node, you're going to have, realistically, 6 degrees of freedom. Right? It can move in 3 linear degrees of freedom in space and 3 rotational degrees of freedom in space. And each one of those has to be represented by an equation. So if it has 10,000 nodes, it's 60,000 simultaneous equations to solve. We don't want to do that, right? Not at all, okay? So we don't. But that's basically the game that's played. Now, that we're going to go through, and these of course form into, they write these in matrix form, and they have names for them. They call the stiffness equation and the displacement vectors and all those kinds of things. It doesn't really matter. It's just expansion of simple things. Now, in typical FEA classes that are taught in mechanical engineering programs, I would get an FEA textbook, and I would dive down into wonderful things about the how we can come up with and derive these shape functions, and we could spend several weeks doing that. And there's only one thing I know for sure.
Never use it again?
You'll never use it again. Yes. That is the odds of you ever deriving a shape function in your life, I hate to tell you, is essentially zero. Okay? It's not because you're not capable of deriving those,
Could be.
because you are, but the people who do that, first of all, work for the FEA companies, make the code, and secondly, those are people who spent way too many years going to graduate school and ME programs and got good at that stuff, right? So while you can get good at it, that's what you're going to have to do if you want to go write shape functions for FEA equations, because there are people who have done it, and that's who they hire, right, for that kind of job. But that's not what most of us do. Most of us want to use this as a tool, right? We want to use this stuff as a tool to basically solve for this, usually the stresses, sometimes the displacement, in parts that are more complicated than we want to deal with, right? That are too complicated for us, that are more complicated. So we're not really concerned too much about what's going on under the hood. I have to show you a little bit of it. Now, there's a kind of an interesting how do I phrase this? It's kind of an interesting quandary, I guess I will phrase, in that it actually winds up that what we would think would be hard problems are easy, and what we would think easy problems are actually wind up being harder. And that is, I said we take a solid, we break it into elements, we break it into nodes. We also can do this with a surface. Okay? And we can do this with a beam or a truss. And we can make this same thing. We can turn it into elements. We can turn those, well, we usually turn it into nodes, populate with nodes, and then turn it into elements. We put the thing back together. Now, if we think about this is a beam element here, and even though it lives in 3D space, we're going to define this as a 1D element. Okay. And by 1D, what I mean is that a beam element can be described by a length. It's one dimension. It has a length. It has no area. It has no volume. So typical 1D elements usually have two nodes like this, the endpoints. They can have three. You can put one in the middle there. People do make mathematical formulations with three. There are some advantages to that. They represent curves better. Now, you can always basically get the same functionality by doubling the number of nodes in that, right? Just add the number of nodes, doubling the number of elements. There are some advantages to having multiple element nodes. The mathematical representations get more complex, but can get more accurate. Okay? So we're going to call these 1D elements. Now, and surfaces, we're going to call these 2D elements. And we're going to, even though they also exist in the 3D space, because these 2D elements are going to have an area, right? They don't have a volume, but they have an area, right? They can confine themselves in space. And of course, 3D solids, we're going to have 3D elements. And that's because they, of course, contain a volume. All the 3D elements are going to define some sort of volume, and we're going to basically build or representation of our part that we're trying to analyze out of these elemental volumes. That necessarily results in some error, some discretion error, right? Because we can't represent it exactly, right? We're not representing curve shapes, other kinds of things. We're having to put points out there and make linear approximations on things. That's what we get to do. Now, the reason I mention this up here is because, in general, we live in a 3D world. So it doesn't matter whether it's a beam or a surface or a solid, they all have volume, right? Everything, all our parts have volume. If they don't have volume, they're pretty useless, right? They don't have any strength because they got nothing, right? So everything we build is 3D. Right? And furthermore, everything we analyze is 3D. So if I have an elemental representation that only has a length, that means that I have to tell the computer everything it needs to know about the other two dimensions. Because it needs to know those in order to calculate do the proper mathematics. So when we say we have a 1D element, what we've done is that means we're going to tell the computer about what are the other things. This typically involves, well, it always involves material properties, but also involves the cross-sectional properties, moments and products of inertias, other kinds of things, where the centroid is, other kinds of things like that, right? For these kinds of 1D elements. For 2D elements that have an area, again, we don't have things like that. Everything has a volume. We need to make, in order to make them 3D, typically we give them a thickness. Usually that's uniform. There are some element types that will support tapering variable thicknesses, but they're kind of rare. Most of the time it's constant thickness, and we're dealing with that. So again, this is a little easier. For 3D elements, all we have to do is give it some notion of material properties. We can calculate all the rest of it. Okay. So that's the options that are available to us in these. Now, for that reason, it's usually easiest to start. While most people like to start with truss elements, I start with solid elements because it's usually easier to think about them, right? The computer will go through and mesh your thing, create a collection of elements, which we're going to call a mesh. It's the representation of your component in elemental form, right? It'll go through and measure your thing in things that hold volume. Now, there are all different kinds of elements that out there that hold volume, many different types. Okay, and there are many different ways of creating meshes, and people get really religious about them and go, some of these are better than others. If you ever talk to stress guys, they're going to go all, oh, I want to do it this way, I want to do it that way, and they'll give you some long-winded explanation, which means they like doing it that way. Okay. In general, in SolidWorks makes the simplest possible elements that it can. That's what it does. I'm okay with that, actually. Not necessarily the most accurate, but they make the simplest one possible. Okay. For solid elements, the very simplest thing you can do, well, let's go the other way. For beam elements, right, the very simplest thing you can have is two nodes, right? Okay, and what do you get? You get this thing over here, right? That's a beam element, right? Two nodes and a line. How about for a surface element? What's the simplest thing I can do that contains area? Triangle. So we get Okay, it's the very simplest thing. There is a restriction on that. Points can't be in a line. They're in a line, doesn't contain any area. Furthermore, it really doesn't like it if these triangles get skewed. You might think of what it's going to do here. It's basically going to turn this into 3 springs. So calculate the displacement on those. That's fine when there's nice angles between the springs. But what happens when the thing looks like this? Come on. Okay. All of a sudden, minor variations in these result in quite significant errors. And they're not exact. None of these are exact. They're all approximations. More approximate. This is what we refer to as a bad aspect ratio. The element is distorted. We don't like those because they give us bad results. Okay. The results are not particularly accurate. They can get really bad. For solids, we of course call those triangles. We can do other things. There are what are called quads. Some people, okay. There are a lot of people that like quads. They're very, very fond of them because they actually, mathematically, they get quite complex because you can put the extra relationships in crosswise. In addition to having springs all the way around the outside, you could put the extra relationships in crosswise, and as such they get more accurate. Problem is that in general it's hard to make a quad measure. Okay, people try, but to try to make a quad measure doesn't, how do you make squares go around circles and holes and other kinds of things? There's geometry that gets hard to do that. When you have triangles, you can do anything, right? And as the computer graphics guys do all the time, because that's all the computer graphics guys do is output triangles. And if you play video games, what are they outputting to your screen? They're just outputting a whole bunch of triangles. That's all they do. Right? Okay. Stream triangles as fast as they can. Okay, for solids, what are we going to do? Cube. Yeah. Well, you want the simplest. Yeah, so the simplest is, what do? We take a triangle and we get one more point. Right, so I have a triangle, let's say in a plane, and then I get a point that's out of the plane. Right, and this is a tetrahedral. Okay? That's the simplest one, and that's what SolidWorks does. Usually all of them will do as a default. Some of them will try to. Again, like triangles, they're not as good as higher forms. We can do bricks, right, and hexagons and other kinds of higher forms. People like bricks, things that look like cubes or sort of square things, because again, you can put cross elements in there, cross mathematical relationships that make them more accurately. Okay. So that's sort of the overview of the class, or the FEA stuff, and then we'll play with it a little bit here. I did put these all up on Blackboard, so if you get a bad copy of it, which since our printer is not happy with the life, but you can complain about them. Okay, so, what's the thing? Okay.
It's terrible.
Yeah, isn't that bad? Yeah. Fortunately, I don't think it's on the front page, so it probably doesn't matter very much. Okay.
Oh, yeah, it's just homework policies. And
Yeah,
exams,
and-
what's gonna be on the exam.
Minor details.
You have it on Blackboard, so.
I know, it's right there.
Yeah, I have, she's trying to give me grief and I'm taking a little bit, but only a little bit,
Only
right?
a little bit.
Right,
I'm
so
only
it's-
fishing out a little bit.
that's true. So, okay, as usual, I'm here before class. There's, I have some books that I was gonna bring up, but forgot them this morning, so, can't get good instructors, along with some of your assignments from last quarter, so can't get good instructors. There is no textbook for this class, okay? Mostly because I'm not real fond of the formal ME textbooks get really heavy into theory, and the other ones, the less formal ones, while somewhat helpful, are, I guess I'm just not really fond of. I did specify Randy Shee's book. He's a OIT professor down in Klamath Falls. He writes these sort of computer instruction books, which are, open this menu, click on this thing, do this. So if you are struggling with SolidWorks or you're struggling with the FEA package, go ahead and buy it. It's cheap, right? And it will sort of take you, and I don't really care if you get this one or one like it, okay? There are other people, the SRC, they make a whole bunch of SolidWorks like books. They're 30 or 40 bucks. I mean, they're not hugely expensive. At least I think that's what they are. Tell me if I'm wrong. There may be one that, I have 17 up there, so there may be, I'm sure there's an 18 version that's newer, because things have changed a little bit, and I'm fine with that. Go ahead and get the newer one, right? Don't get the old one, because we are by definition using that stuff. There is a book that I am fond of, Building Better Products with FEA by Adams and Ashkenazi. Okay. It's actually a really interesting book. I took a lot of the class out of that. But it winds up being somewhat hard to find, and when you do, it's expensive. It can be, I've seen it in the somewhat rare occasions I see it on Amazon, it's in the over $200 number, so it's like, okay, I'm not going to do that. And it's more in line if you want to dive in a little bit deeper than we're going in here in this class. If you want to sort of get further into what's going on, they have a lot of stuff in there. It's a lot of good stuff. For software, I am going to demonstrate SolidWorks. Okay, SolidWorks, the student edition of SolidWorks has an FEA package in it that's actually pretty good. It started out as a FEA package called Cosmos M that was purchased by SolidWorks before they decided before they got eaten by Dassault. And it was a standalone FEA package that was used, and it's actually a reasonable FEA package. I am not religious about either CAD packages or FEA packages. I don't care what you use. Okay, all of them should give you roughly the same quality results. We're not going to do anything fancy or tricky. The reason people like the big boys, MSC Nastran and ANSYS and what's the third one? It'll come to me. It's with an A. Abacus. Yes, the reason those get the big bucks is typically because they develop element types that are desirable for special circumstances in industry. So they'll develop special elements for layered composite, or they'll develop special elements, like Abacus is known for doing special element types that do really well for plastic deformation. Okay, and if you do really well for plastic deformation, then you can do crash simulation, because what you do is you push on the part a little bit and you see what bends, then you push a little bit more and you see what bends, and you push a little bit more and you see what bends. And that's how you do all those weird crash simulations, right? You keep starting from the prior place, seeing how that does. And the Abacus makes an awful lot of money doing that kind of analysis work. Now, we're not going to do anything that fancy. We're going to play with the simple stuff. 90+ percent of what we're going to do is just linear statics. And everybody does linear statics. Right? It's just we assume the material behaves linear. We assume it's isentropic. The material property is the same in all directions. We're going to assume that that it doesn't yield. Right? We're not going to do any post-yielding behavior and other kinds of stuff like that because, frankly, those get ugly. Right? They get ugly really quick. And not that the SolidWorks package doesn't do those, but there's in a beginning course in finite element, we certainly don't need to get in the hard stuff to start with. So I'm going to do SolidWorks. If you want to do CATIA or something else, that's fine, but you're on your own. Okay? I always have one or two that wants to run off and do CATIA. Fine, go for it. They traditionally have made it about halfway through the class and then go, you know, the CATIA FEA package really sucks. Well, that's what I thought it did. That's why I quit using it. But okay, I don't do that anymore. But that's okay. Anyway, that's the in general the textbook and the software on this. There's grading. Okay, we're going to have assignments. I'll give you an assignment every week. There are 9 assignments. You get to go model stuff and give me results. Okay. And you actually get to give me formal reports. I insist upon formal reports, and they must have conclusions. Okay? You must actually have learned something from your model. Okay? Fortunately, as I will tell you, that's easy. Okay? Or as I'll show you, that's easy. It's not that hard to do. There's a couple of projects in here, because after all, you're not mechanical engineers if we don't design mechanical things. So we're going to have you design some mechanical things. Did that scare everybody? I can't scare you anymore? I'm going to have to work harder at it, aren't I? Okay. I think working harder is a good idea. Okay. So the
Oh my God, we're so scared.
okay, there we go. So what we're going to basically, for a little bit of schedule, what we're going to do is we're going to work on 3 weeks of solids. Okay? We're going to play with solids for 3 weeks and try to get the basics down playing with solids, because frankly, they're the easiest to do. Right? They're the easiest and most straightforward to do. Then we're going to go start playing with some 2D elements, some shell elements. We'll talk about why we use shell elements, where we would use shell elements. There's actually a lot of things you'd think, oh, can't we do everything as solids? No, you can't. Okay? And we'll talk a lot about why you can't, and you can't, because your results will be really, not only will they be really complex, but they'll be crappy results. And then we'll talk a bit about trusses and beams, and we'll move off hopefully into buckling and contact stresses. Okay? That we do a little bit of buckling and a little bit of contract stresses. Okay? In those. Okay, so that's the class. Straightforward? I just give you assignments, you go home and do them, right? Okay?
So no in-class test or anything, so project.
At least not for this quarter. There are always surprises.
Hi.
You had to ask.
Was there?
I was preparing myself.
Has there ever been a class with me that you haven't been a little bit surprised? Okay. Or were you pre-terrorized enough to where it was the worst?
Yes to both.
Okay. And you're working on that, keeping it with Bashara too here, aren't you? So that's okay. So with that, I'm going to move on and let's see if I can't hand out the first assignment here, which is, by the way, on Blackboard. If If you want them, I will endeavor to keep them on Blackboard. And these actually don't have weird printing problems. So I have these, which have to be the easiest things that are possible to model. If I could come up with an easier thing to model, I guess I could come up with a slightly easier thing to model, but it would only be slightly easier. Did everybody get one? Yep. Okay. Okay, so what we have is let's see if I can in here we have a beam. Okay, a beam, and this one happens to be a simply supported beam. Okay. Simply supported beam, right? It has a distributed load on it. It's a rectangular cross section. Can I get an easier problem than that? Nah, then it's actually harder to load then. This is actually easier. It's actually harder to constrain and load if it's circular. But it does take one less dimension, I'll grant you that, Brad. So, okay. But it makes other parts harder, so okay. So this is the only thing, we have a 3-foot long beam, we got some distributed load on it, okay, and so let's just go play with how we at least can think about doing this. I won't do it exactly, but we'll get something similar. So I get SolidWorks here, hopefully. See if I get SolidWorks to chug alive for me. One never knows with SolidWorks. It used to work very reliably, and then it got bought by Dassault. Okay. Isn't that not, did I say that out loud? I guess I did.
Fairly accurate.
Okay, so we have parts out here, come on. And we get, yours may or may not look like mine, depending on how many, SolidWorks tends to remember the way you configured it from prior sessions and things like that. That doesn't, you're not necessarily the same, but we're gonna model some things here, and so of course I'm gonna have to model a 3-foot beam. So let's go to sketch here. I need to pick a plane. I'll pick the right plane, and we'll sketch on it. I'm going to sketch some rectangular section, right? Like that. Okay, I'm going to dimension it up. All right. Okay. So I have a 1" by 4" thing. Is that not what it is? Let's make it 1 1/4. Just a 1.2, just because we can have some fun then. Okay, and we get out of the sketch, right? We have this thing, we extrude it, right? We're going to extrude the darn thing. How long do I want to extrude it? Well, let's make it 40 inches. Just because we can. Okay. Okay, and I have a beam. Now, wasn't that hard? No.
Just different.
And your size.
Just different than Katia.
Oh, we did different than Katia. Okay. Okay. Yeah, okay. Well, I think that it's probably closer than Katia before was.
Oh, by far.
Yes, yes, so that, because I think Katia V5, they sort of tried to steal the interface from SolidWorks, is what I think they tried to do. Not entirely successfully, but tried, so, okay. But anyway, that's, you don't have to use SolidWorks, you can use Katia. I'm not,
I'm gonna try to, yeah, I'll try.
okay, I'm not feeling it, but that's.
I have so many brain cells learning.
Well, I don't know about that, Matt. You know, you need to, you know, it's like going to the gym. You need to exercise them more. You need to exercise them more. Build up some bigger ones. Okay, so once we have a model that's, yes. The one that says, no, that's visualization. There's one that says, over there. That's SolidWorks. You need to find one that's the SolidWorks up there. Okay, so we've made the model here, right? And it's not, I'll let you guys go home and play with making the model. It's not necessarily hard to do. We're making the play with the model. So far, that's just solid modeling, right? That's something that nothing really to do with the class. We just got a solid here that looks like what we would like it to look like. Okay, the FEA package that we get at in it's under one of SolidWorks simulations. That is under under the add-in tag, they have simulation. See, mine has, on the tabs up on the bottom, it says simulation. Yours probably doesn't. Okay, if it doesn't, it should be under the add-in tabs here. There's one that says SolidWorks simulation. Okay. You can also get up here at the top in simulation, if you have it up at the top. But if you click on the simulation, we get a new study, or if you're on add-ons, or like at the top up here, you can get simulation too. If you go to the file at the top, up at the very top up here, you can run down to simulation and get new study. Either way will work. We get new study, okay? It pops a menu over here that talks about some of the different kinds of studies we can do. It's not all of them, but it's some of the different kinds of studies we can do, right? And we have statics, we have frequency, we have thermal buckling fatigue, nonlinear and linear dynamic, all kinds of different things for which they have element types for. You can do lots of these. I sometimes don't have a lot of faith in the answers, but that's okay. They're going to give you answers. We can all try to figure out what they're worth. We are, for essentially, again, 97% of this class, we're going to do static analysis. Even if the things are moving, we're going to say they're static and the loads are static, because otherwise life is hard, right? And if they're moving, we're just going to get peak loads on them and go with those. So we're going to do static analysis. We say good, and we get a new set of tabs at the top up here, and we pretty much go down the line. Okay, what is we need to do? If we have a list of things we need to do across the top, the first thing we need to do is typically pick a material. We then have to constrain the part in space so it doesn't rocket off into space. And then we have to put some sort of loads on it. We may or may not have connections, and then we run the study and we have results and all kinds of good things we can look at. Okay, so the first thing is, I'm going to get the part here. We can apply a material. I said it was what, 6061 aluminum. So mine insists upon being steel. I think I want some aluminum. Let's see. I want to go 70-75 just because I could be on
Is that
there.
material library that's already in here in
Yep.
modeling software?
Yep.
Where did you grab?
It's just you select the part on the, no, come on, cancel. Okay. If you just select the part on the top over here, right, and then apply the material. Okay. So once we have that, we have a perfectly fine, we've now given a material that tells me it's 70-75, right? It's a part of 70-75. Now we need to fix it in space. The thing will not, let me phrase this correctly. The part must be completely constrained in space. Okay, that is it can't have any dimension that it's not constrained in,
or it, because the forces will never completely sum to zero in any given direction. And so if there's a direction that it's unconstrained in, that little bit of force coupled with basically frictionless surface will allow it to go rocketing off in space, and you'll get undefined variables in there somewhere. So all FEA models must be constrained in space. Okay, they have to be constrained in space, and that's the fixturing,
what we call fixturing or boundary conditions. And in my personal experience, that's that's the hardest thing to get reasonable in FEA, is the boundary conditions. If you don't have the rest of it is trivial, but the boundary conditions are where all the art is. Okay? And there's fundamentally one rule that I use in FEA is that I don't trust any results that are by a boundary condition. Just don't trust them at all. I have no faith in the answer. Okay? Because they're almost always wrong. Okay. So that's because it's very hard to replicate real world boundary conditions. So in this particular case, we can click on this thing. If you click on this thing up here that says fixture advisor, it'll pop some sort of wizard thing that tries to drag you through things, but I do not find it helpful. So I tend to go click on the arrows underneath these because the wizards and advisors are not particularly useful. And let's see, what do we want to do? Well, we'll take some guesses here. Looks like I got a hinge, right? I mean, what is my thing? I got the kind of, if I look at my problem over here, my definition, I got one of those roller things at this end, right? And I got a kind of a fixed support at this end, right? Okay, so let's go give that a whirl. Okay, so I'll go, oh, okay. Well, shoot, here's one of these roller things. Okay, I'll pick on that one. Oh, okay. So let's go try that over there, right?
You apply it to the side.
Well, go with me a little bit here.
Okay.
Okay, and so because I mean it needed a face to apply it to.
Oh, I see.
It wouldn't go to anything else.
Choose the edge.
It wouldn't let me choose the edge.
Why are your arrows pointing inward?
Well, that's the way it is constraining it.
Mine are not.
It doesn't matter. Okay, and then let's go. Well, here's one of those fixed ones. I can fix the geometry, and that'll actually let me go in here and fix that edge down there. Okay.
Fix will let you do the edge, but the roller will let you pick a face.
Yeah, it has to pick a face.
Okay.
At least that's my. Now we can go back and look at it if we want to, because fixtures we do have them down here. We can always go in and edit them. But see, this one, it's really wanting a face. You know, I don't think it's going to let me. If I try to pick an edge down there, it's just not happy with it,
Yeah,
right?
it's not even
Right.
trying.
It's not even gonna let anything. Okay, so we're gonna go with this for the first order, and then we'll do a load, right? And again, you could pop the advisor, but I advise you to just go click on the down arrow. And in this particular case, we're going to use a force on this. So we get a down arrow and a force. Right, and we can pick one of those. We'll get a force. Do we want the force normal to the surface or have some particular direction? Well, I'm just going to pick it over here. I want it down to the surface. I do want to put it in English units, and I want it to be what? 160 pounds per inch times 36, or in my case 40. 160 enter 40 times. That's 160 enter 40 times. That's a bit better number. How about 6,400? Okay. Okay. That's a load on there. I got the obviously you have to go in and calculate it from your 160 pounds per inch, linear inch, and then the rest of it, and you're gonna get a slightly different number than me, because that's just the way we have. Okay.
What units did you do? Like,
Well, if it's in English, you wanna do it in English, right? If it's in metric, you wanna do it in metric. Okay. Now I have a solid model of a beam there that has some constraints on it that will certainly keep it from moving out in space. And that will also has some loads on it, so it's actually going to do something. If I don't put any loads on it, it's not going to do anything, or it's just going to sit there and look like a block of stuff, which is kind of, well, might be interesting, but most likely boring. Okay. Great. So we have this, and we've moved across our first three things coming in from our new study. We have a material, we have some fixtures, we have some loads. We don't have any connections because we only have one part in here, so we don't really need any connections. We don't really have a shell manager. So now we get into the meshing part. Now you can just push run this study and it will run. I don't ever do this. I mesh this things. And so you can come over here and you can do a create the mesh, which is typically what I do. And you create the mesh and you get a mesh density graph here. From coarse to fine. I tend to run it down coarse initially, and for a couple of reasons. First of all, I like to see if it runs faster if there's fewer calculations that it has to do. And I also like to check and see how my results are doing. And we oftentimes do this with what's known as a convergence study. So I can, once I pick a coarse one here and say go, it will chug off and it gives me a mesh, right? It has a mesh. These are the elements that it has created in there, right? It's created a bunch of nodes with a bunch of elements in there. If I come over here to my mesh and I right click on it, I can get details. And it says that for this particular part, it's created 3,000 nodes with 1,700 elements. Right? Okay? And most of them are pretty good. So they have pretty good aspect ratios. It's pretty happy in there. Maximum aspect ratio is a little over 3. So the aspect ratio is the relationship of the biggest side to the littlest side of a triangle, right? So you'd like those not to be horribly off, right? Okay, so have a mesh, okay? And I'm happy, I love this. Let's go ahead and run the study. It runs the study, it chugs and it goes kaboom. And we have results. That's fun. Of course, I'm in English, and it's giving me results that are in
French.
Well, yes, Newton meters. So if I want to change those, I can come over here to the stress, where we have results now over here. Or I can right click on them and edit the definition. So you right click on the stress and edit the definition. That'll allow me to change it. One of the things I can go is, okay, let me get PSI instead of Newton meters. Von Mises is fine. That gives me where we do a lot of von Mises. There are other options there, lots of other options. I can do von Mises. I can do principal stresses. I can do normal stresses and shear stresses. But von Mises is usually the most useful. Okay, so now we have it's getting up there to what? 129,000 psi. Okay, that's probably not a good thing, right? I tend to look at them, first of all, in the flat side. Come on, get out of the way. Okay, I like to look it up in the flat side over here. And the first thing I notice is that my boundary conditions are wrong. Yes, wrong. And they're wrong because, well, it's supposed to be supported at two ends, right? And I don't know about you, but it sure doesn't look like it's supported over at this end. Right? So that boundary condition looks like it's just bad, right? And that's just the first rule of any of this. When you get done with it and you push run, you look at it and go, does it make sense? And look at it carefully. Okay? Because does it make sense? Is it reflective of what I expect to see? And if it's not, why not? And don't assume that it's right, because it almost never is. In this particular case, I screwed this up, and what it did, my sliding condition is keeping this edge vertical, right? It allows it to move on this edge, but of course I push the dickens out of it, right? And what happens? So I go, okay, well, that's not good. So, okay, I better go back and fix this. So, okay, we go back to our fixtures here. Don't like that roller slide thing. Let's get rid of it. That was a terrible thing to do, delete. So, do you really want to delete the load fixture? Yes, I do. I don't like you at all. So, let's go get some others. Fixture advisors. Well, fixed hinge. We could try a fixed hinge, but it's not a fixed hinge. It's got to move. Right? Okay. Well, so, well, roller slider, fixed geometry. It's not really fixed geometry either. Guess we're going to have to go to advanced fixtures. I'll have to tell you a little hint here. When I do boundary conditions, I always start at advanced fixtures, because the other ones for most of the time don't work with a darn anyway. So I tend to always start here. This gives you as much control as you're going to get over anything. Okay, so what we have in here, this is advanced fixtures. There's some fancy ones here: symmetry, cyclical symmetry, cylindrical faces. I tend to use reference geometry. It defaults to that, and it is the most useful. So I'm on this use reference geometry up over here, right? And what it does is it gives me what do I want to constrain, and then what geometry do I want to use to identify it. Well, I want to constrain the edge. So I'm going to zoom in here to the edge, and I'm going to constrain that very edge, right? Because that edge is sitting on the knife edge of the support, right? So that's a perfectly fine thing to constrain. Now, how am I going to constrain it? Well, I want to constrain it so it doesn't move up and down, right? And probably the easiest way to do it is the reference geometry that they're looking for. I click on the next box below. This is where I specify the reference geometry. You can really pick any of them, but I'm sort of methodical. And so I'm going to pick this bottom one here. And the reason I picked the bottom one is I want to constrain the out of plane displacement. It's allowed to move in. This beam is allowed to move in this plane. It can move this way, and it can move this way, right? It's just not allowed to move in the Y direction. That's the allowable constraints that it has. Okay? So, and then I can come down here on my constraints over here, and I have translations that I can fix. And there's one that's in plane, another that's the other direction in plane, and the third is the one that's out of plane. So it's always the easiest to fix the one that's out of plane, right? And so I tend to pick reference planes where I'm going to fix the out of plane one, because then I don't have to try to figure out which one's that direction and which one's that direction in plane. It's not hard. They give you arrows, but it's not bad. So I can click on this, and you see I get arrows here that are forcing my way up there, which is exactly what I want it to do. Right? It doesn't displace anything at all. It just sits there, right? Gives me exactly what I want to do. And so I can say, okay, everybody sort of see that and got that there? Okay? So, now I can come back, I have funny yellow arrows here because I changed my model. Yes, I did. Let's go ahead and rerun this thing. I don't need to remesh it, rerun it, and now it looks a little bit better, right? So I always look at them in the orthographic projection so I can see, does it make a little bit of sense at least, right? Because if it doesn't make sense in the orthographic projection, I'm in trouble. Okay, well, at least the shape is looking right. Right?
So you
Why is
couldn't
it-
have,
Go ahead, sir.
well, you couldn't have put the roller constraint on the bottom thing? Would
Nope.
it have constrained the entire thing?
Yep.
Oh, really?
Yep,
Why
Yep.
did you do that?
because it allows you to pick a face, and the face goes all the way across there. And even if you had a small section, it wouldn't work right. Okay? And the reason why it wouldn't work right is because even if it had a small section, we try to keep that small section flat. It wouldn't let it rotate. Okay? Okay, it's very, very easy to over-constrain things. Yes?
Why is the distributed load all wonky now?
Oh, it's just what they do. I don't really care about what the arrows look like. That's what the arrows are. They sort of put them up there, and how many they put on there and where they put them depends upon the local scale. So they move around a lot.
Okay.
Okay?
So
I don't really care too much about
When
that.
we're looking at it and making sure that it makes sense, that's not one of the things.
That's not one of the things that we're worried about. Yeah, I don't worry about what their arrows that are indicating the load are saying. Okay, because that's just their arrows that they've put on there. You can make them bigger or smaller, but okay. So I'm still getting a big stress here, 1.5 million. And where is that big stress? Well, one guess, but it's not over there.